In a dismantling yard outside Yokohama, a technician winches a V8 out of a wrecked Lexus that has just crossed 480,000 kilometers, and the crew barely reacts. They've seen this before. The block gets set aside not for scrap, but for export. Because everyone on that floor already knows what's inside it will look closer to new than to worn out. It's a pattern that's followed Japanese V8s from the 1990s for 3 decades now. And the deeper you dig into why these engines refuse to die, the more it looks like the outcome of one very specific, very expensive decision made by a handful of engineers who were never told to stop. That decision starts with a project Toyota launched in secret in 1983, internally called F1, flagship number 1. Chairman Eiji Toyota wanted a luxury sedan that could go head-to-head with Mercedes-Benz and BMW. And he gave his engineering team something almost no automaker gives an engineering team: no budget ceiling and no deadline. Over the following 6 years, more than 1,400 engineers and 60 designers built 900 experimental engines and tested prototypes across 1.67 million miles of real-world driving, from frozen roads in northern Sweden to the baking asphalt of the Arizona desert. In one test, they left prototypes sitting in that desert heat for 3 months, alongside competitors from BMW and Mercedes. When the team came back, the German cars showed visible sun and sand damage. The Japanese prototype looked nearly untouched. What came out of that process was the 1UZ FE, a 4.0-liter naturally aspirated all-aluminum V8 with a forged steel crankshaft carrying 8 counterweights instead of the standard 6, main bearing caps secured with 6 crossbolts instead of 4, forged connecting rods, and oil squirters installed under each piston purely to manage heat that the engine would rarely, if ever, generate in real driving. None of it was necessary to make 250 horsepower at a relaxed 5,400 RPM. All of it was there because the engineers had been told to build the best engine in the world and interpreted that instruction literally. That single V8 became the template for how Japanese manufacturers approached big displacement engines through the rest of the decade. And the reasoning behind it is the first real answer to why these engines don't die. They were never designed to operate anywhere near their actual mechanical limits. A modern V8, or really any modern engine, is tuned close to the edge of what its components can handle, because every gram of unnecessary material costs fuel economy, and every ounce of unused strength is money left on the table. The 1990s Japanese V8s were built the opposite way. Engineers oversized the bearings, overbuilt the bottom end, and left enormous mechanical margin between what the engine could survive and what it would ever actually be asked to do in a customer's driveway. That margin doesn't just prevent failure, it changes how the engine ages. Components with that much slack settle into a fully bedded state early, then simply stay there, because normal driving never approaches the stress that would push them past it. Toyota didn't stop with the 1UZ. The larger 2UZ FE, a 4.7-liter V8 built for trucks and SUVs like the Land Cruiser and Tundra, made an even more deliberate trade-off. Where the 1UZ used an aluminum block with cast iron cylinder liners to save weight in a sedan, the 2UZ went with a full cast iron block because the engineers knew this engine would spend its life towing, hauling, and idling for hours in traffic. And iron holds its geometry under sustained heat and mechanical stress in a way aluminum simply doesn't. Mechanics who work on these trucks today describe the bottom end of the 2UZ as close to immortal. Nissan took a similar approach with the VQ Series V6 and its bigger V8 siblings, wrapping the block in cooling jackets generous enough to prevent the hot spots that cause head gasket failure and cylinder wall distortion in less carefully engineered engines. Across every manufacturer, the pattern repeats. Cast iron where aluminum would have been lighter and cheaper, forged internals where cast components would have passed every safety inspection, oil coolers standard on engines that would statistically never need one. The second reason these V8s hold up traces back to how the cars around them were actually driven, and that has as much to do with Japan's regulatory environment as it does with the engines themselves. Japan enforces one of the strictest vehicle inspection systems in the world, called Shaken, requiring every car to pass a rigorous safety and emissions inspection every 2 years after its 3rd year on the road. The inspections are expensive, and for an older car, the repair costs needed to pass Shaken can approach the value of the vehicle itself. That math pushes Japanese owners to retire cars far earlier than owners in most other countries would. A Lexus or Toyota V8 with 60,000 kilometers and no real complaints often gets sent to auction rather than kept and repaired. What that means for the engines, still on the road, is that most of them were driven gently, maintained on strict dealership schedules, and never pushed anywhere close to the abuse a budget-conscious owner in another country might put a car through. When mechanics pull one of these V8s apart decades later, they're not looking at an engine that survived hard use. They're looking at an engine that barely experienced hard use in the first place, running on top of a design that had enormous margin to begin with. Those retired low-mileage V8s don't disappear once they leave Japanese roads. They flow into one of the largest used engine export markets on the planet, dismantled and shipped whole or in sections to garages in Australia, the Middle East, Southeast Asia, and East Africa. Mechanics overseas installing these engines into pickup trucks, taxis, and project cars report the same thing over and over. Units that arrive looking barely broken in and then run for hundreds of thousands more kilometers with nothing more than routine maintenance. That's not a marketing claim from a single dismantler trying to move inventory. It's a pattern confirmed independently by mechanics on different continents who have no reason to agree with each other except that they're looking at the same physical evidence. There's a third factor, and it's about the fuel system architecture these engines used, which turns out to matter more than almost anything else on this list. Every one of these 1990s V8s used port injection, spraying fuel into the intake port just upstream of the valve, rather than directly into the combustion chamber, the way nearly every modern engine does today. Gasoline acts as a solvent, and every time the engine ran, fuel washed across the back of the intake valve, continuously rinsing away the oily vapor that drifts up from the crankcase ventilation system. Nobody designed that as a cleaning mechanism. It was a side effect of where the injector happened to sit, and it quietly kept these engines' intake tracks clean for their entire service life without anyone doing anything extra. Modern direct injected engines lost that accidental benefit when manufacturers moved the injector inside the cylinder to gain efficiency and power density, and now those intake valves sit dry, coated over years by baked-on carbon with nothing washing it away. That's a large part of why a 30-year-old Japanese V8 can show a cleaner intake tract than an engine built 15 years later, and it's also why the older design keeps looking better rather than worse the longer it runs. Every kilometer driven is another wash cycle scrubbing the valves clean, so the engine's internal condition doesn't just hold steady with age, it keeps getting reinforced by the very act of driving it. Oil analysis tells a related story. Mechanics servicing these older V8s at high mileage routinely describe the drained oil as looking nearly identical to what comes out of a low mileage example, provided change intervals were respected, because there's very little metal shedding into the oil once the internals have fully bedded in and combustion stays clean enough to keep soot loading low. That stands in sharp contrast to some direct injected engines today, where fuel from cold starts and rich combustion cycles can seep past the rings and dilute the oil in the crankcase, thinning the very film every bearing and camshaft surface depends on. One design is fighting a slow chemical battle against its own oil from the day it's built. The other simply isn't, and that absence of an ongoing fight is a large part of why these old V8s seem to stay in a kind of mechanical steady state decade after decade, rather than slowly declining the way most machinery does. Timing hardware follows the same logic. Most of these engines used hardened steel timing chains rather than rubber belts, and a chain running in clean, stable oil can outlast almost every other component in the engine. Mechanics tearing down these V8s at high mileage routinely find chains, guides, and tensioners that show so little wear, it's hard to believe they're original. The chain isn't defying physics. It's simply operating inside a lubrication environment that never degraded the way oil in some modern engines can, so it keeps doing its job without the erosion that would normally accompany that much time in service. If you're finding this as interesting as I did digging into it, take a second and subscribe. This channel breaks down exactly why certain engines defy the odds while everything built around them eventually gives out. It's worth being honest that not every V8 from this era was flawless, and that survivorship plays some role in the reputation these engines carry today. The units still running now, still getting pulled and shipped overseas, are survivors by definition. Any 1990s V8 with a hidden weakness or a manufacturing flaw mostly failed and got scrapped decades ago, long before anyone today would think to compare it against a modern engine. What's left in circulation is a filtered population, the strongest examples from an already conservative design philosophy, and that filtering makes the average surviving engine look even more impressive than the average engine actually was when it rolled off the line. But that bias sits on top of something real. These engines weren't just lucky to survive. They were built with enough margin that survival was the expected outcome rather than the exception. And that's a meaningfully different starting point than most modern engines have. What makes all of this worth paying attention to today isn't nostalgia for a bygone decade. It's that the industry already knows what it lost when it moved away from this approach, and parts of it are quietly trying to get it back. Toyota's dual injection systems, pairing old-style port injectors with modern direct injectors on the same engine, exist specifically to recreate the accidental valve washing effect that engines like the 1UZ FIs had by default. Oil manufacturers reformulating specifications to resist deposit formation are chasing the same chemical stability these older engines achieved without trying. Nobody at Toyota or Nissan today has forgotten how to build an engine this durable. The constraint isn't knowledge, it's cost and regulation. because an engine engineered with this much margin is heavier, more expensive to produce, and harder to justify against fuel economy targets that didn't exist in 1990. So the hidden reason these Japanese V8s refuse to die isn't one single trick buried in the metal. It's the compounding effect of several decisions made at the same moment in automotive history. Engineers given no budget ceiling and no deadline, a regulatory environment that pushed the cleanest, gentlest driven examples into export markets, and a fuel delivery architecture that happened to keep cleaning itself every single time the car was driven. Strip away any one of those factors and the story looks ordinary. Put all three together, running through the same block for 3 decades, and you get an engine that a dismantling crew in Yokohama can pull out of a 500,000-kilometer car and set aside without a second thought. Because they already know exactly what they're going to find when they open it up.